Howdy guys, we're here to talk about molar volume and gas density. This is going to be video number 2 in our section, and you should be doing this on February 20th. Our homework tonight is going to be the second page off of our worksheet packet, and I'll show you which ones to work on. Okay, so just start with me and think in a hypothetical sense. Now, we do know that we have our equation of PV equals nRT. That's our ideal gas law. And this is a great gas law that describes just the physical properties of gases. Now, just hypothetically say that if we were at STP, that means that our pressure would be 1 atmosphere, and we don't know our volume, and we don't know our moles either. But since I know my pressure, I can find out my value of R. My value of R is 0.0821 because that's my correct value for R for atmospheres. And then my temperature is 273 Kelvin. Okay. So, well, 1 atmosphere right here is really, that's 1 times V is really just V. So I'll simplify that to V equals N times 0.0821 times 273 Kelvin. Okay, well, now we have 2 numbers here that can just be, and they're just 2 numbers, so, and they're multiplying together, so I'll just multiply. And what we find is that V equals N times about 22.4. Okay. And if we get our variables on the same side, and we end up with V over N is 22.4. So our volume divided by our number of moles is 22.4. So another way to say that is there are 22.4 liters, remember that's our unit for volume, per 1 mole. And this ends up being a basic true fact at STP. For any gas, the volume of any gas at STP is 22.4 liters. Notice I did say that it is at STP. STP is really important, and this is also for any gas. And that makes sense. If you remember your kinetic molecular theory from the previous unit, we know that the unit of the gas molecules themselves actually occupy a negligible volume or a 0 volume. So it's the empty space that makes up the volume. So it really doesn't matter which gas molecule it is. It could be oxygen, could be nitrogen, could be hydrogen sulfide. It doesn't really matter because it's the empty space that's making up the volume. So your notes on page 2 will actually really describe this in very short detail, but why don't we go ahead and go through some examples. Example 12 says that what is the volume of 0.35 moles of O2 at STP? So since it is at STP, I can just use 0.35 moles of O2, and I can just convert it. And so my conversion factor right here, remember that 1 mole of any gas is 22.4 liters. So that is my conversion factor right here. So I need to make sure I put moles of O2 on the bottom so they cancel out, and I have liters of O2 here. So there's 22.4 liters in 1 mole. So 0.35 times 22.4 is going to be 7.84, but I need to approximate that to 2 sig figs since I have 2 sig figs in my original answer. So I get 7.8 liters of O2. And that's my answer there. Now, example number 13. is going to use another conversion factor. A chemical reaction produced 125 milliliters of CO2 at STP. What is the mass of the gas produced? So we have to remember two different conversion factors. Remember that when we're doing this, we have to be careful about our volume. Notice that here, our units are in milliliters, and we need to make sure that our units are always in liters, or else our calculations don't work right. So remember that there are 1,000 milliliters in 1 liter. You should know that by now. You should know that a milli means 1,000. There are 1,000 years in a millennium, and a millipede has 1,000 legs, so there's 1,000 milliliters in 1 liter. And we do know that our other conversion factor of 1 mole is 22.4 liters. So start with what we know is 125 milliliters of CO2. And I need to make sure I fix it and convert milliliters to liters. So convert milliliters to liters by just dividing by 1,000. That will give me a decimal value in my correct units of liters. So if I stop there, I'd only have liters. And then I can convert liters to moles. So liters of CO2 can be converted to moles of CO2. And there are 22.4 liters in 1 mole. And that's not what it asked me, though. It asked me for the mass. So I need to make sure I convert moles to grams. So moles of CO2 goes on bottom because I want my units to cancel, and change it to grams. So there's one more conversion factor I'm having to use. I get this one off the periodic table because that's what G stands for. Go to the periodic table, and I find out that there's 44 grams in 1 mole of CO2. So 125 times 1 times 1 times 44 divided by 1,000 divided by 22.4 divided by 1 will give me 0.24553, and I need to approximate that to 0.246 grams of CO2. By the way, you see me approximating a lot of numbers right here, this little step. You don't have to do that. If you can just go ahead and round yourself, that's fine, but I do that just so you guys will see that I'm rounding to the correct sig figs. In this case, it's 3 sig figs. So example number 14 says, what volume in liters would 56.2 grams of CH4 occupy? So I need to first change grams to moles, and then I'll just change moles to liters. That's really what I'm going to do. So I'll take 56.2 grams of CH4, and I need to convert grams to moles. Of CH4, and the molar mass of CH4 is going to be 16 grams per 1 mole. Found that from the periodic table. And then I need to convert moles to liters. So I've got moles here, and I need to put moles on bottom so it can cancel and get liters. So I get CH4, and I get 22.4. And so multiplying 56.2 times 1 times 22.4 divided by 16 divided by 1 will give me 78.68, approximated to 78.7 liters of CH4. All right, good to go. So at this point, I want y'all to stop with the notes, and I want you to go straight to your worksheets and apply what you've learned. I want y'all to do questions 1, 2 on this worksheet, and then 3, and then also question number 4 that's on the back side. They should be real simple conversions, just converting moles to liters, or in this case, converting grams You'll have to convert grams to moles, and then convert it to liters. Okay. Don't worry about 5 and 6 at the moment. You'll have to watch the rest of the video for that one. All right, we're back to our notes on page 2 at the bottom, where we've learned what the molar volume is, and now we're going to apply that to density. Since we already know that 1 mole of a gas of any gas at STP is 22.4 liters, we can actually figure out the density of the gas at STP rather easy. What we've remember that density is simply mass divided by volume, and you can rearrange the variables and figure out that the density is going to be the molar mass divided by 22.4 liters. So it's really density is the molecular weight. I like to write it as capital N, capital W divided by 22.4. You'll figure, I'll show you why I write it as M and W later. So to do example 15, I want to calculate the density of SO2 gas at STP. So I need to find the molecular weight first. The molecular weight of SO2 is just going to be the molar mass of sulfur, which is 32, plus 2 times the molar mass of oxygen, which is 16. Found those from the periodic table. And that ends up to be a total molar mass of 64 grams per mole. And I'm going to write all over this, so forget about this right now. Now what you're going to do is, if we take our density, the density is going to be my molecular weight, which is 64 grams per mole. And that means I'm going to divide it by 22.4 liters. Now remember that this is, that's how many liters are in 1 mole, right? So if you look at the units right here, we've got 64 grams per mole and 22.4 liters per mole. Well, those per moles right here are actually kind of unnecessary. So what I can actually do is I figure out that the density is 64 divided by 22.4 grams per liter, which is the unit for density. Awesome. It is the mass divided by volume. So I end up with my density as 22.9 grams per liter, and that's my answer. So really, you just have to take the molecular weight and divide by 22.4, and you find your answer. So before I do example number 16, I've cleaned this up a little bit to show you what the work is actually necessary to do, is to show what I've just circled in green. That's you don't have to do all the extra junk that I did. I was just trying to show you where it came from. So on your test, though, make sure you show that. So example number 16 says, what is the molar mass of a gas that has a density of 1.28 grams per liter at STP? So my density at STP, make sure you make that notation at STP, is going to be my molecular weight divided by 22.4, right? Well, so I already know my density is 1.28 grams per liter. Well, now I got to figure out my molecular weight. So 22.4. All right. So just take both sides and multiply by 22.4. I'll go ahead and show that. 22.4. And that will cancel it out. And I find out that my molecular weight is going to be 28.7 grams per mole. Okay, grams per mole. Remember, that's the That is the molecular weight or the molar mass. I hope I've made myself, I hope I haven't confused y'all when I say molecular weight and molar mass. Um, Molar mass and molecular weight are exactly the same. They are synonyms, but sometimes different teachers or different professors use different ones. So I hope that's okay. So we've covered what gas density is at STP, but could you find it at any other value besides STP? And the answer is yes. If you remember a real quick equation, remember that the density is the mass divided by volume, and that's going to be helpful later. And you can also remember a cool quick equation that is the molar mass of a gas equals the density times R times T divided by P, or the molecular weight, kitty cat, sweeps his dirt over his pee. Okay, that's a real quick thing, and that's actually easy to memorize, and because you will have to do that because it's not on the AP formula chart or the IB formula chart, and it won't be given to you on the test. So that's real helpful though to be able to solve these kinds of problems. So example number 19 is going to ask us what is the molar mass of a gas if 0.628 grams of the gas occupies a volume of 150 milliliters at 25 degrees Celsius and 7,456 millimeters of mercury pressure. So it wants to know the molar mass, so also known as molecular weight. So that's what I want to know. And I know the mass and I know the volume. Now, hold on a second. Remember, your volume is your standard unit that you always want to use for volume in this unit is always going to be liters. And this is given to me in milliliters. So 1,000 milliliters is 1 liter. So go ahead and fix that and convert it to 0.150 liters. An easy way to do that is to take the decimal place and move it 3 places to the left. That will convert it. And then we also need to make sure we convert our Kelvin, our temperature, to Kelvin. So 25 degrees Celsius becomes 298 Kelvin. Well, so we know the molecular weight is my dirt over the P, right? DRT over P. So I need to figure out the density because it doesn't actually explicitly tell me what the density is, but I know that density is going to be the mass divided by the volume, which I know the mass is 6.28 grams, and my volume is 0.150 liters. And that is going to be 4.1867. I know it's not the correct number of sig figs, but I'm not done yet, so I'm going to wait to round. So now I know the density. I know R because I know my pressure. I know R never changes, and T is my temperature. I know that one, and I know my pressure. So, and now I'm ready to go to be able to substitute everything in. 4.1867 grams per liter times my value of R, which is going to be 62.4 this time because I'm using the millimeters of mercury. All right, and that's going to be liters dot millimeters of mercury. I know that's small, divided by moles dot Kelvin. And then my temperature is going to be 298 Kelvin. All divided by my pressure, which is 7,456 millimeters of mercury. All right, once that's done, I can figure out my molar mass, which is going to be, before I round, is going to be 10.441, but I need to approximate that to 10. And I'm going to leave that decimal place there to make sure, let me know that that 0 is significant, because I want 2 sig figs in my answer, because my temperature is in 25 degrees Celsius, so that's 2 sig figs. So that's 10 grams per mole. That's my unit of molecular weight, and I'm done with that example. Example number 20 is going to show us what is the density of a sample of NH3 gas if the pressure is 0.93 atmospheres and the temperature is 63.0 degrees Celsius. Right off the bat, go ahead and convert your Celsius to Kelvin. So that's going to be 336 Kelvin. And I know my pressure, I know my temperature, and I can figure out the molar mass or the molecular weight. Simple enough. The molecular weight of NH3 is going to be the molar mass of nitrogen, which is 14, plus 3 times the molar mass of hydrogen, which is 1. So it's really going to be 17 grams per mole. Okay. So if we know that the molecular weight kitty cat sweeps his dirt over his pee, then we have 17 is my molecular weight, grams per mole. And my density is unknown, so that's a little d, times my unit of R. Unit of R is going to be 0.0821 this time because I'm using pressure in this example. And times my temperature, which is 336, and divided by my pressure, which is 0.93. Algebraically, you should be able to solve that, but I'll go ahead and help y'all out. What you should do is take 0.93 and move it over to the left side of the equation. So you have 0.93 times 17 equals D times 0.0821 times 336. And then I need to move these two constants over to the left side of the equation as well, which means I need to divide by those. So what I'm going to end up with is 0.93 Okay, and I've got that there, and what I have to do is type it all in the calculator, and I get 0.57 grams per liter, and that's always going to be my unit for density. To do your practice problems on density, you'll have to go to this very first page of your worksheet packet called the Ideal Gas Law Worksheet, and if you go to questions 8, 9, and 10, they all talk about density. Okay, so you're going to want to do those, and then you're also going to want to do questions 5 and 6 that are on the second page, which is the molar calculations right there, and that will be your density practice. All right, thank y'all.